Hey folks, my name is Nathan Johnston. Welcome to lecture 3 of vector calculus, which is all about tangent lines. So the idea today is we're going to talk about how you can construct the tangent line to a path or a curve, which the idea there is you've got a path or a curve that's moving through space, and you look at one particular point on it. You want to find the line that goes through that point and has the exact same slope as the curve at that point. So it just kind of comes in, touches the curve, and then goes off from there at the same slope. And you probably already know how to do this for plane curves in R2. So a curve that's the graph of a function, y equals f of x. But let's talk about how to do this in general in any number of dimensions, and even if your curve is defined parametrically. Okay, so to connect this with stuff that we did last class, remember we constructed this velocity vector. And the velocity vector, we talked about how its length is the speed at which the particle is moving along the curve. Okay, but the direction of this velocity vector is also important. The direction of the velocity vector, remember, it's pointing in the same direction that the particle is moving along the curve. Okay, so sort of the setup here is you've got some curve that's being traced out by a particular particle. It's moving along this curve. The velocity vector is always going to be pointing sort of straight forward, the direction of motion of the particle at that point in time. Okay, and we're going to use this to construct the tangent line to this curve or to this path. Okay, so the setup here is that we're trying to construct a line that's going through a particular point on a curve, and also it has the same slope as the curve at that point. Okay, so let's start off with just reminding you what's a line look like in sort of this formalism that we're using here. Remember, in our very first lecture, we looked at equations of this form. This is a line, right? It's a line going in the direction of the vector A that's offset from the origin by this vector B. Okay, so this is a path that's going to trace out what's going to become our tangent line. Okay, we want this line to go through some particular point on the path. So what I'm going to do is I'm going to pick a particular time value, t0, a particular input to the path, and say, okay, well, the line at that time has to be the exact same vector as the path at that time as well. In other words, like if I imagine a particle moving along the path and a particle moving along the line, those particles are going to collide at time t equals 0. Okay, so yeah, so that tangent line, it's got to touch the path or touch the curve traced out by the path at time t equals t0. Okay, and the last thing that we want to happen is we want them to have the same slope as each other. Okay, we want them to be pointing in the same direction. In other words, these two particles, when they touch, they'd better be pointing the same way. So I'm going to require that their velocity vectors are the same as each other. I'm going to require that L prime at this time when they're colliding, it's the same as F prime at the time when they're colliding. Okay, so the tangent line, it points in the same direction as the path. Okay, so geometrically, what we just did, what we just described is, well, sort of this picture here. We've got a particle that's moving along a curve, and then at some particular time, t0, well, this tangent line, there's a particle moving along it, and at that time, t0, those particles collide at this point here, and because they're moving in the exact same direction, they've got the same velocity vector as well. Okay, so that's what conditions 2 and 3 here are. Same position, same velocity at that time t0, and then this one up here is just because it's the equation of a line. Okay, so what we're going to do now is we're going to take these equations and we're going to use them to figure out what these vectors A and B are. Okay, so we're going to use these equations down here. We're going to substitute them in to equation 1 to figure out what A and B are. And the first observation I'm going to make is that, okay, L prime at t0, I can figure out what that is rather directly just by taking this formula for L of t and then computing its derivative or computing its velocity, right? Remember, the way that you compute the velocity is you look at each entry and take the derivative with respect to t. And if you do that, all that's going to be left in each entry is the corresponding entry of A. Okay, so what happens is the velocity of this vector is just the vector A itself. Okay, so if we trace these three equations through, we get that F prime equals L prime equals the vector A itself. So great, we figured out what A is. We're halfway there. All that we got to do now is figure out what B is, and then we'll have a nice formula for the equation of our tangent line. Okay, so what we're going to do there is we're going to plug this equation into equation 1 as well now. Okay, and when we do that, what do we end up with? Okay, well, we've got L of t equals some junk. Well, I'm going to plug in t equals t0 first off. So this t becomes a t0. That t also becomes a t0. And then I've got L of t0 over here. Well, L of t0 is f of t0. So I'm just turning it into f of t0 on the left-hand side. And then on the right-hand side, what's this become? Well, t, again, I subbed in t0 for t. And then a, well, we just talked about how f prime at t0 equals a. So I'm going to replace a by that, f prime at t0. And then plus b. B is all that's left, okay? And b is the only unknown there. So I can take this equation down here, rearrange, and solve for b, okay? And when I do that, well, I'll just move everything else to the other side. And I'm going to get b equals f of t0 minus t0 times f prime at t0 minus the velocity vector. Okay, and now, great, I've got a formula for A. A is this f prime. B is this thing here. I can plug these A and B values into this formula for the tangent line. And when I do that, I learn that my tangent line, it looks like this. Okay, my tangent line is L of t equals t minus t0 times the velocity vector plus the position vector, which makes some sort of sense, right? Remember when we were doing this, we said that the tangent line, it should be going in the same direction as the path f itself, and that's what this is doing, right? Like, where's the parameter? Here, it's in front of this thing, so, and this is the velocity vector. So what direction is it going in? Well, the same direction as f. And then plus, this is like the offset. This is how far away from the origin it is. Well, L is the same amount away from the origin as f is at t0, okay? Now, the only thing that we're going to do to simplify this a little bit more is we're going to change parameters a little bit, okay? I'm going to change it so that this t minus t0 is just one single thing. So it's just parameter times f prime plus f, okay? And well, the main reason I'm doing that is just to clean it up a little bit. I'm going to say s is t minus t0, and sort of the reason that I'm free to do that is it's still going to trace out the same line. It's just sort of scaled back a little bit, okay? Instead of the particle being up here, it's down here, or vice versa, okay? I'm just changing where the particle is on the line at a particular point in time, okay? And when I do that, okay, this new parameter s, it's going to have s equals 0 at this point, rather than t equals t0 at this point. Okay, so when I'm measuring how much time has passed on the line, if I say, 0 seconds has passed, that means I'm at this intersection point. 1 second, like s equals 1, is 1 second farther along the line. It's like t0 plus 1, and so on. So it's just a reparameterization. It's just a rescaling, sort of the time parameter, of the input. Okay, and when I do that, my tangent line has this really nice form. Okay, my tangent line, it's s times the velocity vector plus the position vector. Okay, you can't get much simpler than that. Okay, so anyway, let's do a couple examples. Let's compute some stuff. Okay, so let's go back to a helix. We talked about a helix in our very first lecture. So this is that same helix. Okay, so f of t equals a times cos t plus a times sine, a times cos t, a sine t, and then b times t. Okay, those are the three entries. It's a curve in R3. Okay, A is the radius of the helix, and B is how stretched out it is. And the question is, well, find a formula for all the tangent lines of this path. And in particular, can you tell me what the tangent line at that point, negative a0 b times pi, is? Okay, so let's start off with, let's just find a formula for a tangent line in general for this path here, okay? And let's go back to our formula. How do we do this? Well, we're gonna need to compute the velocity. So let's compute the velocity of this path. In other words, let's take a derivative, okay? Compute f prime, and I mean, it's just take the derivative of each entry. A times cos t, the cos becomes a negative sign, this sign over here becomes a cos, and this b times t just becomes a b, right? The t becomes a 1. So there's our velocity vector. Now what we're going to do is we're going to plug a particular value t0 into it, and we're going to multiply it by s and add f of t0, right? We're just going to plop all the pieces into this formula, and we know all the pieces to plop into the formula now, okay? So our tangent vector, formula, and what's it look like? Well, it's just this thing with all the t's replaced by t0s. That's all that is. And then this piece over here, this is f of t0. That's just this thing here with all the t's replaced by t0s. Okay, and that's it. That's our tangent line if we want it to go through f of t0. Okay, now, if we want to find this particular tangent line, the tangent line going through that particular point, we've got to figure out what the t0 corresponding to that point is. Okay, so what you do is you've got to look back at your formula for the helix, or whatever your path is, and try to figure out what t value I could plug in here to get this point out. And for this particular curve, that's probably easiest to do by looking at the third entry. I want b times t to equal b times pi. Oh, well, I should choose my t value to be pi itself. Okay, so I'm going to choose t0 to be pi. I'm just going to plug in that everywhere in my tangent line formula, and that's going to give me my tangent line. Okay, so when I do that, just replace all the t0s by pi's. Okay, here where I've got a sine of t0, that sine of pi, oh, that's 0. Here where I've got a cos of t0, that's -1, right? Because cos of pi is -1, so I get negative a in the second entry. And similar things over here. Cos of pi becomes a -1, sine of pi becomes a 0, b times t0 becomes b times pi. Okay, so that's my formula for the tangent line. And if I like, I can combine that all into one vector, right? Just add up entries. 0 plus negative a is negative a. S times negative a plus 0 is negative s times a, and so on for the third entry. Okay, so that's my formula for the tangent line that goes through the particular point negative a 0 b times pi. Okay. All right. Now, there's one thing that I sort of glossed over when I showed you the formula for the tangent line, and that is in this theorem here, we made this assumption that the velocity is non-zero at the spot where you're constructing the tangent line. And you might be wondering, why on earth did we make that assumption? Like, where does that come into play? And the reason we need that assumption is that in this formula here, if f prime at t0 equals 0, then what happens is this goes away. So you have s times 0. All the stuff involving s goes away. It's just the 0 vector. So you just have L of s equals f at t0. And that's not the equation of a line, right? It doesn't depend on s. The particle's not moving along that at all. It's not tracing out a line. It's just stuck at a single point. Okay, so if the velocity is 0 at a point, you can't construct a tangent line there. Okay, so let's see an example where this goes wrong. Okay, so what we're going to do is we've got a path here. Let's try to construct the tangent line at the point 0, 0, 0. Okay, so first off, velocity, right? Just compute the velocity. You need that for tangent lines. Just always do it. Okay, so take the derivative of each entry, use the power rule on each of them. That's what we get as our velocity vector. And now, okay, what's our t naught value? Okay, like what value of t am I plugging in? Well, I want it to occur at this point. So I go back to my function f. I ask what value of t would I have to plug in here to get this point. And of course, it's just t equals 0, right? So that's what I'm plugging into my velocity vector to try to construct the tangent line. Okay, but when I plug that t0 into the velocity vector, I get the 0 vector, right? All of these pieces become 0. So my theorem, I can't use my theorem. Okay, the velocity is 0. There's no tangent line to construct from there. Okay, but here's the kind of weird thing. I claim the curve that this path traces out, I claim that curve actually does have a tangent line. Okay, so I want to draw a distinction here. There's a slight difference between the tangent line of a path and the tangent line of a curve. Okay, what we just showed is no, that path does not have a tangent line. And if you look at the picture here, okay, the reason for that is as the particle's moving along the curve, okay, right, when it's crossing the origin, its velocity very briefly, instantaneously goes down to 0. The particle stops just for the briefest of moments, okay? And at that moment, no, there's no direction anymore, okay? So it doesn't make sense to talk about a tangent line through that point in time. Okay, there's no line that's doing the same thing because it's not moving at that spot. Okay, but there is a tangent line to the curve. Okay, and based on the picture here, I mean, if I wiggle this around, yeah, it looks like it's smooth there. It looks like there should be a tangent line. How do we actually convince ourselves of it rigorously, though? And the trick that works in this particular case is we can just reparameterize the curve. I can find a different parameterization of this exact same curve, but a different parameterization or a different path that actually does have a tangent line. Okay, so that's what we're going to do here. Okay, and the trick that I'm going to use is I'm going to introduce a new parameter u here, which is just going to be t cubed. Okay, I'm just going to choose this first entry here to be my new parameter. Okay, and this works out fairly well in this particular example because the cubing function, right, t cubed, that's an invertible function. For every value of t, there's exactly one value of u, and vice versa. For every value of u, there's exactly one value of t. Okay, so all that's happening here is, I'm sort of distorting the domain of the function, but then still mapping all of those points to the same points in the output. Okay, you can sort of think of it as like this curve that F defined. That curve is like a piece of string, and we had beads laid out on that string. By reparametrizing or changing the input variable here, we're moving the beads around on the string, but we're not changing the orientation of the string itself. Like I'm not bending the string in a different way. It's still the same curve. I'm just moving along it at a different rate. Okay, so anyway, let's do this. Let's now sort of look at what this path looks like in terms of u. Okay, so what I'm going to do is I'm going to say, okay, g of u, that's going to be the path that moves along the same curve, but is defined in terms of u this time. So for example, the first entry is t cubed. No, it's u now. Okay, the first entry is u. Okay, what should the second entry be? How do I get t to the power 5? Well, just take this defining equation here and raise it to the power 5/3. Okay, I'm going to have t to the power 5 on the right. Yay, middle entry is u to the power 5/3. Okay, and similarly for the third entry, how do I get to t to the power 7? Just raise this equation to the power 7/3, and you get u to the 7/3 in the third entry. So that's going to trace out the same curve. Okay, now we can retry our tangent line calculation. Okay, what's the velocity vector? Well, derivative of each of these, you just get 1, then 5/3, and subtract 1 off the exponent, and 7/3, subtract 1 off the exponent. And the difference this time is that at u equals 0, which is where I get this point in my function g, at u equals 0, this velocity vector is non-zero. Okay, so I don't have that same problem anymore. Okay, because, well, I mean, if you look back at that curve and how is this particle moving along the curve, how is this path tracing out that curve, this time when it goes through the origin, it doesn't stop for a break, right? The particle is not stopping as it goes through the origin. Okay, so there's no problem this time. I can just use my formula for the tangent line. It's just s times the velocity plus the position vector, and you throw all that together. Okay, my velocity vector, when I plug in u equals 0, is just 1, 0, 0. And then my position vector, when I plug in 0, is just 0, 0, 0. I add those up and simplify a little bit. All I get is the vector s, 0, 0. And if you think about this, like what's this tracing out as s changes? Chasing out the x-axis, right? Because it can have any number in that first entry, and the other two entries are both 0. So the tangent line to this curve and the path g, that's the x-axis. All right, cool beans. So yeah, so sometimes you can have a path where even though the path itself doesn't have a tangent line, the curve that traces out does. All right, sometimes even the curve itself doesn't have a tangent line, even though on the surface it looks like it should, even though sort of the functions that define the different coordinates in your path look really, really nice. Even sometimes then, the curve won't have a tangent line. So let's go through an example like that. So let's explain why the path, again, is going to R3, so it's going to be sort of a curve in three-dimensional space. Explain why that does not have a tangent line at the point 0, 0, 0. Okay, so step one, let's maybe just check the path itself. Let's verify that the path doesn't have a tangent line there. Okay, and so the velocity vector, same thing as always. Take the derivative of each of the entries. And then, okay, which value of t am I plugging into it? Well, I want to know which value of t makes this function go through the point 0, 0, 0, and it's just t equals 0 again, right? Okay, so I'm plugging 0 into my velocity vector to find out what the velocity at this point is, and it's just, oh, it's 0, 0, 0 again. Okay, so the velocity at that point is 0. No, there's no tangent line there, okay? At least not for the path. How do I convince myself that there's no tangent line there, even for the curve itself, not just the path? Like, how do I know that, oh, maybe I can just reparametrize it, like in the previous example, and get a tangent line? No, that's never going to work. How do I know that? Okay, so let's look at this geometrically. Okay, we're going to plop over to the graph here, and notice there's something very different going on this time. This time, it looks like there's a cusp at the origin. It looks like the curve's sort of doing a very sharp change of direction at the origin. Okay, how do I pin this down and really convince myself that that's what's happening and that there's no tangent line? Okay, and here's the trick. What I'm going to do is I'm going to give names to each of these entries. Okay, the first entry is the x coordinate, so I'm going to call that x. X is t cubed. Second entry is the y coordinate, that's t squared. Third entry is the z coordinate, so z is t to the power 5. Okay, and now I'm going to think about what happens if I take this curve and just look down on it. I'm just looking at the floor, looking at the xy plane. Okay, what's this curve look like there? And to answer that question, I can just ask, well, okay, what's y in terms of x? Like if I was just to plot like this on the xy plane, like I'm sort of used to from single variable calculus courses, what would that look like? What's y in terms of x? And we'll notice that if I just take x and raise it to the power 2/3, then I get y, right? If I do t cubed to the power 2/3, I get t squared. Okay, so what that tells me is that y is x to the 2/3. And that's exactly the function, that's the graph that you're looking at when you look down on the floor here, when you look at the graph, the 3D plot down from above. Okay, and now this tells us that there's something kind of weird going on, right? Because this, as a single variable function, this function does not have a tangent line at the origin. Okay, this almost convinces me that there's not a tangent line, because if there were a tangent line in like the three-dimensional picture, tangent line of the path, then when I looked down at things, looked down at the floor, so I just see a two-dimensional xy plane, then that tangent line, it must look like a tangent line for the two-dimensional curve as well. But this two-dimensional curve, it doesn't have a tangent line at the origin because it's not differentiable there. Okay, except there's one minor exception to that, and that is if the tangent line were pointing straight up and down, then when I looked down at that picture, I wouldn't see the tangent line. The tangent line would just look like a dot. Okay, so the only special case that I have to rule out separately from this is what if the tangent line is the z-axis? Okay, but that's not too hard. There's a separate argument that you can do, and if you do the same sort of reasoning, except instead of with the xy plane, you do it with the yz plane, you'll find that it can't possibly have a tangent line in that plane either. So there just can't be a tangent line at all. Okay, like there's no tangent line for this curve whatsoever. So we're just done with it, okay? And sort of the point here is that for curves, for paths to be nice, really you do need this derivative not being zero, this velocity vector never hitting zero, because in examples like this, they can lead to things like cusps and other weird behavior that you wouldn't necessarily expect can happen from nice, pretty differentiable functions, from polynomials even. Okay, let's talk about one final way of thinking about the tangent line. Let's talk about how to think about it physically, okay? And the idea here is if you've got a path, okay, that's a particle moving along a curve, and we can think of it as it's moving along the curve because some forces are acting on it, okay? So the example from last class was that, we had a ball on the end of a string that was being spun around. Maybe another example is that, okay, you've got a particle moving through the air and it curves down because gravity's pulling it down. Gravity's the force acting on it. And the tangent line tells you what happens to that particle. How does it continue moving if that force suddenly vanishes? So the example from last class was, what if that string suddenly breaks and the ball, goes off in a straight line in whatever direction it's trying to move at that point, okay? Or, in this example here, we've got someone being fired from a cannon, and then unfortunately, halfway through being fired from the cannon, the Earth magically vanishes, okay? So all of a sudden, there's no Earth anymore, therefore no more gravity, and then what happens from there is they don't keep curving down because there's no more gravity pulling them down, so they just go off in the direction of the velocity vector, or equivalently, the direction of the tangent line, rather than curving down. So that's how you can think about the tangent line. It's just where would the particle keep on moving if there were no more forces acting on it, if it was just free to do its own thing, inertia sort of stuff. Okay, let's do one final computational example playing around with this idea, okay? So my son likes it when I hold onto his hands and spin him around so that his feet lift up in the air and he's spinning around in a circle. This is not actually my son here, of course. It's surprisingly hard to take a photo while both of your hands are holding someone else's hands. So we've just got stock photography here, but that's the idea, okay? So I'm holding his hands and I'm walking forward as I spin him around and hold his hands like this. So like sort of my path, you can imagine it's sort of like a spiral path, okay? It's sort of spinning around, but it's also moving in one direction as I spin him around. Okay, so that's the path that my son takes, and then I'm the world's worst father, and what happens is after 5 seconds, I say, no, I'm done with this. I let go of him, and he goes flying off from that point. And the question is, where's he gonna be 1 second after that? After 1 second of flying through the air, where is he going to be? Okay, assuming that he hasn't hit the ground before that or anything like that, okay, to stop his motion. Okay, so the idea is he's going to be following the spiral path. I let go of him. Now he just follows the tangent line. Where does he end up after 1 second traveling along that tangent line? Okay, so I've got to compute a tangent line, so I need to compute a velocity vector. Here's my function, compute the velocity vector of it, just take a derivative, right? Okay, so derivative of the first entry, cos becomes negative sine. Chain rule gives me an extra 8 out in front. Derivative of the second entry, t becomes a 1, sine becomes a cos, and I get an extra 8 out in front because of the chain rule. Okay, now, I'm going to build the tangent line out of this, so here's my general formula for a tangent line. What's t0? Well, I'm going to build the tangent line going through this point where I let go of them. I'm letting go of them after 5 seconds, so I'm going to choose t0 to be 5. Okay, so I'm going to plug 5 into my f prime and into my f, and when I do that, I get this horrific mess here. Okay, so this is the equation of my tangent line with the parameter s. Okay, fine and dandy. What do I plug into this to actually get my final answer, though? How do I figure out where he is after 1 second on this tangent line? And for this, remember the way we define this parameter here for the tangent line is that describes like at s equals 0, you're at the point where the tangent line hits the original path. Okay, so when s is 0, I'm at f of 5, right? I'm at the t0 point. Okay, so if I go 1 second farther, I should choose s equals 1. Okay, s equals 1 tells me, okay, yeah, I've gone from the point that he was at, and then I followed one copy of the velocity vector. Okay, so what I get then when I plug s equals 1 into this tangent line formula, okay, well, I get velocity vector plus starting position, and I just compute that crap. I plug all of it into a calculator, and I get some vector here. Okay, so I find that, yeah, after 5 seconds plus 1 more second, my son, he ends up at this point here. And like the way to interpret this is that he ends up 6.63 units west or to the left of where I started, and he ends up 1.41 units north or forward from where I started when I started spinning him around. Okay, and here we can sort of see the path that was taken, by my son in this entire thing, and tangent line A just goes back into the left a little bit from where he started. Alrighty, and that's all I've got for today. Thanks for watching, everyone. We'll go on next week, learn about lengths and arc lengths and all that sort of stuff. So I'll see you then for that.